Like in a computer game, for instance, we're usually highlighting the fact that something is broken. Technology plus paternity, technology paradigm. Still that there are pretty clear-cut instances of technological error. The metaphor actually working exactly as intended. In today's episode, we're debuting the
Sorry. Let me back up for a second. When we say something has glitched, like in a computer game for instance, we're usually highlighting the fact that something is broken, or not working as it should. In short, we see glitches as pretty clear-cut instances of technological error. But what if we're wrong about what glitches fundamentally are? What if they're not failure or mistakes, but actually working exactly as intended? On today's episode, we'll get deep in the guts of the question, what even is a glitch, anyway? In her paper, Calculated Error, Glitch Art, Compression, and Digital Materiality, Carleigh Morgan argues that computer glitches are not as random as they appear to be. Contrary to what we naively think, glitches are ordered and shaped by the software and hardware that give rise to them. As a consequence of this, we should reconsider what exactly we talk about when we talk about glitches, most specifically in the context of so-called glitch art. Morgan begins by giving a brief overview of a glitch art technique called compression hacking. Compression hacking, or datamoshing as it's more commonly known, is a glitch art creation technique that, true to its name, involves corrupting compressed video files to create a certain type of visual glitch called a compression artifact. That's the big blocky pixels you're seeing right now. To understand how this glitch works, and a large part of Morgan's argument, I need to explain what exactly is going on here. So, at its core, all data compression is a method of data storage optimization. Morgan actually explains this really well in her paper, so I'm going to borrow her example. Imagine I want to send the following sequence of letters over the phone. AAA, AAA, BAA. Now, I could read each letter in the sequence individually like I just did, but that takes time, and maybe I want to get this information to you as quickly as I can. So how do I shorten this? One way to do it is to just say 7 A's, 1 B, and an A. It takes less time to say, so I have more time for actual conversation. In technological terms, I'm compressing or storing/transmitting all the necessary information using less space. Digital video compression works the same way. Digital video files are made up of two kinds of frames. The first kind, called an iframe, short for initial frame, otherwise known as a keyframe if you have any animation background, is basically a still image that contains all the color and luminescence data for that image for other frames to use as a reference point, or in plainer terms, key off of. The other type of frame, called a P or predictive frame, informs your video player of any changes to the image's compositional arrangement since the previous frame. There's also a type of frame called a B frame, which references both the frame before and after it, but that's not as important for the purposes of Morgan's argument. As you can see in this image, I'm cycling through the I and P frames of the video to show you the relationship between the two. So the way most video compression algorithms work is that they capture only the difference between an I frame and a P frame. Rather than have, say, 10 frames where my pod racer stays in more or less the same spot, and thus have a larger video file, the compression algorithm just takes the difference between the frames, which means broadly that we have less data to deal with and thus a smaller overall file size. What you perceive as motion in a video clip is actually determined by the relationship between sequences of these two frame types mixed together. The compression algorithm just applies rules for how the individual frames in the sequence are stored. With that out of the way, we can talk about datamoshing or compression hacking. The broad strokes of how datamoshing works has to do with messing around with the relationship between I and P frames in a video file. For instance, dropping or deleting a couple of iframes in this video clip means that subsequent P frames don't have accurate data to key off of, so you get an out-of-date reference for the P frames in the sequence, leading to this kind of tearing effect like what you see here. The different types of glitches come about as a result of messing around with the data of these frames and how a video player renders them. This actually touches on an important point in Morgan's paper. These visual glitches might at first blush appear to be random chaos, but this chaos is constrained and ordered by both the compression algorithm itself and the component parts of the image or video in question, along with how the image is displayed at the most basic hardware level. However, Morgan has another interesting point. Just because we view a glitch as a technological failure, it doesn't mean that a technological failure has actually taken place. To think of compression artifacts as glitches in the traditional sense of technological failure, Morgan argues, is to deny both the artistic labor that goes into producing these glitches in an artistic way, and to misunderstand the deeper relationship between visual and technological malfunction. For Morgan, a glitch is indeed a breakdown, but rather than understand that word as invoking the idea of dysfunction, the meaning being gestured towards is more in line with the idea of taking something apart. Compression artifacts, like the one you see in this video, are side effects of using lossy compression algorithms, which don't store the complete amount of data for an image, but rather removes data deemed inessential to save on storage space. To return to the example I gave earlier in the video, imagine I'm once more trying to send you a string of letters over the telephone. This time, though, I'm using a lossy compression algorithm. So where before I would tell you that my string consists of 7 A's, 1 B, and an A, I would instead say something like roughly 8 A's and a B. You can probably see that though this is pretty much the same as the letter sequence in the first example, it seems a little less precise than that first lossless compression technique we used. A similar thing is happening with the glitches in this video. Those chunky or blocky pixels you're seeing are a kind of compression artifact called a macro block. The way macro blocks are produced is due to a step in the compression algorithm called quantization. Normally, the details of individual pixels in a video or image file are captured using a complex range of values. Quantization simplifies this by breaking an image into blocks of pixels and encoding a single value per block. It's the computation equivalent of me saying to you that the sky is bluish today. You know what I mean, but you don't have as good a picture as if I told you the sky is baby blue, for instance. I've simplified, but in doing so, I sacrifice detail. When you datamosh a video by deleting I or P frames, the changes can't really be fixed since you're removing frames that contain the reference data for other parts of the video file. So what you get, in effect, is the algorithm going, I think this chunk of pixels was supposed to be the same color as this other chunk, but this is saying it's a different color. And without those iframes, I can't double check and make sure, so I'll display what it's telling me to display. This is, of course, a simplification because there's a complex interplay between the video frames and compression algorithm that allows these glitches to arise, but it's a good enough explanation for now. The ultimate point, though, is that it is the grid of pixels on your screen that gives the macro blocks their specific appearance. In plainer terms, pixels are the, quote, matter of which digital images are formed and the medium through which an image takes shape, end quote. But pixels by themselves are not the atomic components of a digital image, since they're too small to see with the naked eye. In fact, pixels are tethered to what's called a pixel array, which is what it sounds like, a group of pixels put together. Whatever weird, glitchy effects you're seeing in this video depend on the right group of pixels to activate in the right sort of sequence to achieve the desired effect. In this way, Morgan argues, glitch art imitates failure successfully, rather than relying on outright failure to succeed. The visualization of macro blocks depends on a functioning compression algorithm as well as a functioning pixel grid to geometrically shape the form of the glitch. Thus, these seeming random technological failures are neither random nor failure. They just appear to be those things because we don't have access to the deep internal logic that governs their production and display. The balancing act between the algorithmic dimension and the visual dimension mean that the two layers are interdependent but not behaviorally identical. An error at the algorithmic layer won't always visually manifest. Likewise, visual error is not a reliable indicator of a technological malfunction. And that's the ultimate point. For Morgan, a glitch, as I said above, does not invoke a technological breakdown in the sense of outright failure, but rather is kind of a calculated error that indirectly exposes the computational logic governing the display and realization of these artistic or aesthetic objects. A reconsideration of glitches as aesthetic objects allows us to get clearer on what exactly we're talking about when we talk about the glitch in glitch art.
So,
I really like Morgan's theory. There's a lot to think about, especially with regards to the question of what a glitch is from the ontological or aesthetic perspective. I am, however, curious how Morgan's calculated error view of glitch art would account for my personal favorite glitch art creation technique, databending. Broadly speaking, databending is a method of data corruption where you open a file of one type, say a JPEG image, in a program that doesn't normally handle that data type, let's say a text editor, for instance. My preferred method of databending involves opening an image and video files in Audacity, an open source audio editor. The glitches you're seeing now are a result of this process. Now, Audacity is interesting because it allows you to render any kind of data as an audio waveform. So what you can do is import a video file or image file and use Audacity's built-in effects to alter the characteristics of the waveform, thereby altering the characteristics of your source video or image. However, unlike datamoshing, databending does not depend on just I or P frame alteration to achieve interesting effects. In fact, despite all my investigations into this stuff, it doesn't appear to be dependent on much of anything that I can figure out. While I can figure out what certain effects might be doing to alter the waveform of my image or video, I have zero clue how the alteration to the waveform will affect how the image or video displays. So a top-level explanation like macro blocks or misapplications of a properly functioning compression algorithm isn't open to me because by and large I'm not producing macro blocks and have no idea what, if any, compression algorithm I'm toying with or in what way. Given that my glitches more often than not utterly break the files I'm working with, I would argue that databending is glitch art as manifested technological error and not just the appearance or aesthetic simulation of error governed by a functioning algorithmic layer. To Morgan's credit, I do think that the glitch visualization is constrained by the digital materiality of the pixel grid thesis still holds as an explanation for how these errors display. But the actual mechanistic or algorithmic layer that dictates how these errors form is just not accessible through this type of glitch art creation. Another glitch art technique I sometimes use is called hex glitching. The thumbnail for this video was made with this technique and a little post-processing. Hex glitching, short for hexadecimal, involves using a program called a hex editor to partially disassemble a file into low-level machine language. You can see things like where in memory a certain sequence of bytes might be stored, and you can alter or edit these bytes however you like. Though hex glitching reveals more of a file's inner workings versus databending, it's still difficult if not impossible to figure out how your changes will break a file. Ultimately, I think Morgan built a compelling argument around one very hyper-specific glitch art creation technique. With the wealth of data and resources that can explain the ins and outs of video compression and iframe deletion, datamoshing is an explicable method of glitch art production. And I can see how once you have knowledge of how the different components involved fit together, it does begin to look like you're just simulating error and not actually dealing with real technological failure. But in the techniques outlined above, there are no theoretical resources that can explicate the underlying algorithms governing the production of these glitches. They appear to be genuine cases of glitches as technological failures. Now, in Morgan's favor, I'm sure that there probably is some algorithmic layer governing the whole thing, but the point is that that layer is not open to me. From where I stand, it does look like something is glitching or breaking my file. It is, of course, entirely possible that as our understanding of technology and the algorithms that govern its operation grow and change over time, we might one day arrive at an algorithmic level of explanation for databending or hex glitching as a method of glitch art production, and Morgan's theory will be vindicated. For now, though, I think in the above-mentioned cases, the glitch is a genuine case of technological failure and not just the aesthetic simulation of one. But if nothing else, this is all just food for thought. Thank you for watching and listening, and I'll see you next time.